7.2 Integration by parts. Remember substitution where one of the functions was the derivative of the other function. So we set one equal to u. So in this case, we could say u equals, whichever one, doesn't matter, sine of x. So du equals cosine of x dx. So then, let me see. We will write the sine of u du, and then just integrate it like that. So that equals u plus c, u squared over 2 plus c, which is just sine squared x plus c. And we were done. So, when do we use integration by parts? When the integrand involves products of algebraic and transcendental functions. In other words, do it when you can't set one of the functions equal to u. And when you take the derivative of u, it won't give you the other function that's already in the expression. And then what do I mean by transcendental functions? Well, that's e to the x, or the natural log of x. Okay, so here's an example where I have a product of algebraic functions and transcendental functions. For example, if I have the integral of x squared times e to the x dx, there's my transcendental function, and I do have a product. And if I were to try to use my u substitution, if I set u equal to x squared, then my du would be 2x dx, and there's no way that I can make e to the x look like 2x dx by multiplying it by a single number. And the other way around, if I wanted to make, if I wanted to set u equal to e to the x, well, du equals e to the x dx. So again, there's no way for me to make x squared look like e to the x. So there's no way that I can use the substitution method. So here's our theorem. It says if u and v are functions of x and have continuous derivatives, then we can use this formula right here, which states that the integral of u dv is equal to u times v minus the integral of v du. So we do have some guidelines on how to choose which function is u and which function is dv. So here's our guidelines. We're going to try to let dv be the most complicated part of the integrand, and then we're going to let u be the function whose derivative is simpler than u. So for example, if I had x squared, well, the derivative of x squared is 2x, so 2x is more simple than x squared. So here's our first example. I have the integral of x times e to the x dx, and again, here's our formula as a reminder. So we're gonna let u equal to x, because the derivative of x is 1, and it's a lot more simple than just x by itself. And we're going to let dv equal e to the x dx. So this is u, and this whole part over here is dv. So according to our formula, I need u, which I have over here, and I need v. I do not have v, I have dv, so I will need to integrate. So when I integrate, I get v equals, the integration of e to the x is e to the x plus c. So I put it into my formula because now I have v. So uv, so u is x, v is e to the x plus c minus the integral of e to the x, and then du is dx. This is du, I need a du right there, and we said du is dx. So that's my formula. Again, I have to integrate one more time, so that's going to be x e to the x plus this constant minus e to the x, because the integration of e to the x is just e to the x, plus another c. But they're just constants, so I'm just going to write it as x e to the x minus e to the x plus c to represent that constant, because really this one would be constant 1. So we have constant 1 and constant 2 over here. And we don't know what constant 1 minus constant 2 is, so we're just going to add a constant. And this is my answer, integrated by parts. Okay, I'm sorry for the messy work, messy handwriting. I'm doing this on my iPad, and my stylus is not very good. Example 2. Again, I have two functions that are being multiplied together. One is a transcendental function, that's the natural log x, and the other one is an algebraic function, that's our x squared. So I know that I have to use integration by parts. And just as a reminder, my formula for that is u v minus the integration of dv, then is going to be my x squared dx. X squared dx. That dx from that first function. Okay, which means that I need to integrate both sides. So v, because I need to find v, because I need a v according to my formula. So v is going to be x to the third over 3. And I can write plus c, but I don't really need to because my end expression is going to have that plus c. And I don't need to deal with two constants at a time. So now I'm going to put it in that formula that I gave you earlier. So this formula right here, we're just going to follow it. What is u? U is natural log of x, so natural log of x times v, which is, oops, stylus, x cubed over 3 minus the integration of v, x cubed over 3 times du, and du is right here. So du is 1 over x dx. Oops. So rewrite that a little bit neater. We're going to get x cubed over 3 times the natural log of x minus the integral of this x cancels out with one of these x's. So now I have x squared over 3 dx, which is x cubed over 3 natural log of x minus 1/3 integral of x squared dx. Remember, I can pull out that, or factor out that 1/3 and bring it out to the front of my integral. And then continuing on, we're going to integrate x squared. So we're going to have x cubed over 3 times the natural log of x minus 1/3 times x cubed over 3 plus c, which is going to be, I'm going to write it over here, x cubed over 3 natural log of x minus x cubed over 9 plus c as my final answer. Any questions? I'm not there, so I can't answer them right now. If you have questions, make sure you write them on a sticky note or something so that you remember when I see you again. And you can ask me. Here's a fun one. It's the integration of secant cubed x dx. Okay, for this one, I only see one term, so we're going to do a little bit of math magic. I'm going to rewrite it as the integration of secant squared x times secant x dx. Okay, so now I'm going to choose this one to be my most complicated one. So we're going to say u equals secant x dx, which means that du equals secant x tangent x dx. Just kidding, I don't need my dx in this first one. So then I'm going to choose secant x dx to be my, oops, wrong one. I'm going to choose secant x squared dx to be my dv. So dv equals secant squared x dx. And I'm going to integrate that. So integrating that, we get v equals the integration of secant squared x dx is tangent x. Okay, so this time I'm going to use a structure of my formula for integration by parts, which states that the integration of an algebraic function times my transcendental function equals uv minus the integration of v du. Okay, so my original function, this is my original function right here, which was the integration of secant cubed x dx, which is my original function right here, equals u. What is u again? U is secant x. And then v, what is v? We got tangent x for v minus the integral of v, which is tangent x, du, which is secant x tangent x. dx. I'm running out of room. This is horrible. That was potato. So here I rewrote it, and I'm just going to simplify it a little bit more because I have these two tangent x's. So we have the integration of secant cubed x dx equals secant x tangent x minus the integration of tangent x times tangent x is tangent squared x. So I'm going to write secant x tangent squared x dx And knowing the math magic that I do know about trig identities, I'm going to change tangent squared x into, in terms of secant. So we know that tangent squared x is equal to secant squared x minus 1 from my trigonometric identity. So we have the integration of secant cubed x dx equals secant x tangent x minus the integration of secant x tangent x. Oh, this is going to be, secant x times secant squared x minus 1 dx. Then we're going to distribute that secant into the parentheses to get secant x tangent x minus the integration of secant cubed x plus the integration of secant x. And I need my dx's. So here, I'm going to collect all my like integrals because I have a secant cubed x and I have a secant cubed x on the other side of my equal sign. So what I'm going to do is add that secant cubed x to both sides. So now I'm going to have 2 times the integral of secant cubed x dx equals secant x tangent x plus the integral of secant x dx. So now I just need to integrate that guy. So we're going to get, when I integrate that guy, we're going to get the natural log. So the natural log of secant x plus tangent x plus c. And then all I have to do is get rid of this constant. So it's 2 times that. So it's really 2 times the integral of secant x cubed, or secant cubed x dx equals all of this. So I'm going to divide by 2 everywhere, or multiply by a half. So my final answer will be that the integration of secant cubed x dx, which was my original function, equals 1/2 times secant x tangent x plus 1/2 times the natural log of the absolute value of secant x plus tangent x plus c, which is also divided by 2, but c is just a constant, so it's going to stay a constant. And that is the final answer. That was fun. So here is your homework. It's page 467, number 1 through 10 all, 11 through 29 odd, and this is in your new calculus book, that blue one. Okay? Have a great day.